Alright, time for another draft science video presentation. So we'll start with some comments and see where we go. So one of them is just too useless, this you fail person. Obviously, just a troll account created for some sort of, send a message point. But just useless arguments. But anyway, why do you think a train leaves with twice the velocity? So there's no context to this. There's no it's an hour long videos. This is the best you can do in terms of explaining your point. Doesn't make any sense. Can't make anything out of it. Why not four times? Well, guess what? There's rules. It can't make momentum out of nothing, so it has to be what the spring is producing or the interaction is producing, as I pointed out. Momentum is a fixed amount of something. Should be understood as that. It's like a current. There's actually a video of some guy who's playing with electricity, and trying to make a thing move by having a very high voltage going through a cone, and he can get it to, oscillate, physically move. And it's just kind of funny that I guess to people it's very unintuitive for them to think that electricity is actually the same kind of pressure. It's a force. And that the problem is that what it obviously does is it converts into heat. It doesn't keep its direction very well. So electricity would be able to move things really well. The problem is that it goes in all kinds of directions, which means, it loses its directionality really easily. And you see that because that's one of the liabilities of electricity moving through a circuit is the fact that it's constantly creating heat. Yeah, it's just kind of funny. Anyway, momentum could still be conserved. So again, it's the whole argument of conservation. We know there's no such thing. The language is broken. The idea is that yes, Descartes, everybody sort of agrees that there's a fixed amount of energy in the system, and the energy just moves to different things, and that's it. There's always conserved. There's no, blah blah blah. Now I would argue that in making a gravity argument, it's the one place where maybe it's not conserved. And that's why there is gravity. It's because you actually do have to consume the energy by converting it from a force, moving the speed of light, into a piece of material matter moving much less than the speed of light. And that conversion takes a little energy out of the universe. Now, you could make a counter argument to that statement, but nobody has. Okay. It's all how you think things move. So, I have no understanding of what, you think. What do you think moves an electron? Do you think it's moved because pressure, it interacts with a force that has pressure, little bits of something, or even if it's ether, even if it's a wave? You do understand that it's pressure that's causing it to move, right? I mean, I have no way of it. What do you think happens? What do you think it just actually does do this pull thing where it just imagine it, it's just sitting someplace and there's some invisible, non-physical thing that compels it to go somewhere? Anyway, momentum still could be conserved if the other train bounces backwards. The point is you can't conserve the momentum in the sense you can't use it twice. So if you mean by conservation that, well, I completely transfer the momentum, that is the 5-ton train, going 10 miles an hour becomes a 10-ton train going 5 miles an hour. Now, I've completely transferred all the momentum, so I can't, like New York City also, I can't create a whole bunch of heat. I can't have lost half the kinetic energy somewhere and transferred the energy. You can't do both. Oh, pathetic idiot. Anyway, in fact, the second train could leave with any velocity you wish. Well, I don't even know what does that even mean? And momentum. What are you even talking about? We're talking about real experiments. There's no wishing. You're not allowed to wish it faster or wish it slower. Oh, fuck. I don't know. You're just saying, I mean, how could people be this off the subject? Momentum would in principle be preserved just as long as the first train bounces away at the appropriate speed. Well, the whole point is if it does bounce away, if the 10 mile an hour train becomes a 10-ton 5 mile an hour train, it means you used up all the energy. There is no leftover. So you get it? If you hear sounds and you feel vibrations in the ground, well, it means it didn't leave at 5 miles an hour. It left at 4. Left at some other lower amount of energy because the momentum can't do two things. It can't vibrate the ground and move the other train. Can't do both. All right. Appropriate speed. You see, you have to start with the math. No, you have to start with physical reality. All right, the math doesn't mean anything if you don't have an experiment showing that it means something. The math is just a way of formalizing in most respects, right? 90% of the time, what is math doing? It's just a formalization of geometry. You're just describing a square or a cube or a circle or an arc or some geometric shape. And you've reduced it to a mathematical equation. It makes it understandable in the sense you just do this. Oh, there's a radius, and then I can multiply it by pi, and I can figure out the length of the circumference line. I mean, that's all this is for, math, is to just create some shortcuts in terms of understanding how the sphere will behave, or how something ejected from a spherical object would behave. If I ejected 10 million of them, what would the average be? That's what math is for, you idiot. It's not physics. The math isn't the physics. The physical world is a three-dimensional geometric world, okay? I'm sorry if you don't think that's true, but that's the truth. Anyway, that's the thing that allows you to make a prediction. So more talk about your silly predictions. We have experiments. We don't need to predict anything. What we need to do is analyze the experiments and say, what do they say? So I've already shown the experiment that decisively points out that there's no room for your extra momentum, your extra energy thing. There's no place for it. There's no evidence of it. It can't be detected in actual experiments. I've challenged you to provide me a link to a single solitary experiment in the history of physics demonstrating you collecting this extra energy. Show me one experiment where, yeah, look at it, I collected it. It really exists. There won't be any, because there's none, because it's fallacious nonsense. It's just rubbish. It's religious crapola in the middle of your physics, and that's the simple history. It's right there in your face. There was never any good evidence for it. It was always just a gimmick, and here you are defending a gimmick. For what purpose? It has no evidence, and yet you continue to defend it. Why? Why are you defending something that has no evidence? Zero evidence. Not a single experiment demonstrating it. Show me one fucking experiment. Just one. If you deny this, you are basically denying the possibility of empirical knowledge. Bullshit, I am. I'm saying, show me the experiment. I'm saying, let's do the experiment. Let's throw the 8-pound ball and let's throw the 16-pound ball and see if we can make the 8-pound ball statistically have twice as much energy. Let's see if throwing bowling balls twice the speed, half the mass, at pins means we knock down a lot more pins. Not just a few more pins, twice as many pins. Let's see if we ever come close to that prediction of your theory. Your theory predicts I can knock down twice as many pins throwing that 8-pound ball. Let's see if we can find one human being in the history of mankind that's actually gotten that prediction, has realized it, and has found it to be a true prediction. Your prediction is garbage. The science is garbage. The physics is garbage. The math is garbage. The whole thing is garbage. And for some reason, you are a garbage lover and just wish to sit there and sell garbage to people, which makes you just such a fucking jerk. So anyway, you fail. All right. I'll give you another chance so you can try again, but I think you'll probably fail again. To do anything reasonable, to say anything meaningful, and to show anything at all. Not a solitary piece of evidence will be produced. All right. Yes, remove it, thank you. All right. Oh, that's interesting. Well, I don't want that. I don't want that either. Just put the comments back, you fucking cunt. Anyway. This was a funny comment. I mean, Draft, can you please make a math tutorials? I obviously don't have much respect for most mathematics, and some of it is so convoluted I can't really do a tutorial because it's so convoluted. I mean, all this abstractions, all these unreal numbers. I mean, frankly, it'd be pretty hard to draw the geometry for it. Now, some people have. I mean, Hawthorne made some effort to go through matrices and try to explain how they had some relevance to reality. But some of that stuff is, you're never going to see it. But anyway, I'm not saying never. I mean, and yes, I probably should say something on the subject, and I have. And I'll say more on it right now. But I mean, I'm basically giving you a math tutorial and explaining how their math is arbitrary, made up, religious, and silly. Okay? I mean, it's just a fact of the history. All right, one thing, I mean, just remember, it started off with mv squared. I mean, Huygens said this, did this. But see, Huygens was doing it strictly in the gravitational context, and that's what I was sort of trying to point out to people, that all this just came about because they started thinking what gravity is doing is the same as all other storage devices, like magnetism or some other storage device, a spring, would be behaving the same way magnets are gravity is behaving, and it's not. It's not the same kind of force, and they really just didn't understand how it works, in the sense that they didn't intuitively get the part where gravity, although they say it's 9.8 meters per second squared for everything, no, it's not. In the sense that every object will move at that speed, but every object is absorbing a lot more force depending on its mass. So the heavier you are, the more energy you're collecting. And when you hit the ground, you'll see that more energy. So that all gets sort of connected to this comment, which is good. It gives me an excuse to talk about it. All right. One thing that is unclear, though, is if momentum is energy. Well, I don't even know why you would think it was something other than that. What else could it possibly be? Of what other interest would the concept of momentum have, if not being an explicit statement about something's energy? Why would they call it the quality of motion? Why would they say it? Why would it be meaningful? Why would it mean anything if it's not a description of some sort of energy, something it has? All right, anyway. Velocity times mass, then the units of energy are kilograms per second. So again, this is, you can do all this nuanced crap, but this is where the math breaks down. So I guess I'll go through this. So, I mean, I'm just saying, you do some investigating, you find out some of this stuff. So I've already established that 102 grams, okay, falling 1 meter, okay. So the 102 grams, just being 102 grams of weight, that's a Newton. Okay, so that's what they call a Newton. So if I put 102 grams in your hand, that weight is a Newton. So that's a pressure, right? It's a pounds, and you can just say, well, is it per square inch? When I put it on a surface, right? I can put it per square inch, or I can put it per square centimeter. I can put it, I can shape it into a pinpoint, and then have like 100 or 200 or 300 pounds of pressure per square inch. Because I made the surface so tiny that I'm interacting with, so I can make it so that, that 102 grams will drill a hole right through my hand if I can make that needle sharp enough. But it's just pressure, right? So it's just pounds. So we could convert all of this crap, all of this energy stuff, instead of saying watts and joules, they could just say pounds also. Now, they don't do it. They make it foot pounds per square meter or some other kind of silly notion, but it's just really just telling you how much does it weigh. That's all. So momentum is really just a weight. So you can just say when you're gaining momentum, it's just you're gaining weight in a direction. So if you have momentum of 300 or whatever, let's say, it's a certain amount of pounds that you're actually hitting with. All I do is turn it upside down and you'd get it. Right? See, when it's falling, that's pounds. And somehow when it's going sideways, you don't get, oh yeah, that's pounds too. You're just measuring its capacity to impose pressure. So why didn't physics do this? Why didn't, when they said joule, why didn't they just say, well, a joule equals 400, 1 pound. So let's just make up some number for the sake of the argument, because I don't know the exact number. But the trick is, so I take that 1 Newton, that 102 grams, that's a Newton. And I take the 1 Newton, I drop it 1 meter. Now what they say is, you raise it 1 meter. Well, raising it 1 meter is exactly the same as dropping it 1 meter. Same exact energy, same exact thing. Absolutely no difference. You'll get back from the force exactly what you have to go into the force. So they say raise it 1 meter. Well, why don't I just drop it 1 meter? That's a lot easier. So I can measure that. Raising it 1 meter, I can't tell how much force it takes to throw it a meter high, right? I mean, that's a lot harder to tell. So why don't I just drop it 1 meter? So I drop 102 grams, 1 meter, and the impact, the weight it hits with, that's a joule. So that's a fact. So it's a weight. Clearly, you can know it's a weight, right? So we know that the 102 grams when it hits the ground. So this is the part where, everybody should be able to agree, and this would make physics so much more understandable. And it's just hilarious almost that it's not part of their physics. That they never did this for you. They never made it easy and simple to understand. So, all right, so you take that 102 grams. So let's understand that it's a weird number, right? Because it's not even close to a kilogram, right? It's so you have to put it, converting into pounds is like what? There's 2 kilograms in a pound equals, a pound is 2 kilograms. 2 pounds is 1 kilogram, something like that. But that's not exactly right. It's like 2.6 or so. I don't know what it is exactly. Anyway, all right, so 100 grams is 1/10 of the kilogram, which would make it 1/8 of a pound or something like that. Anyway, so you drop it 1 meter, and the landing force, the momentum, the mv, will equal a certain amount of weight. So when I drop a stick of butter 1 meter, that's 1 joule, and it's also equal. Let's say it's 400 grams, which would be like a half a pound. No, it'd be like a pound. So let's just call it a pound. Let's just make it so we'll make it easy just for the sake of understanding. So that's 1 pound, and that also equals 1 watt. Okay, and it also equals, let's see, what's the other thing it can equal? But anyway, you can get it that it's always just pressure. So when I have 1 watt, I actually have a pound of electricity. You can see it as it's a pound of pressure, electrical pressure. And the problem is in electric current, as I pointed out, the pressure doesn't hit the pins. You know what I mean? The pressure ends up going this way and this way and this way, and it turns into heat. So it starts going in every direction. So it's not very, we don't have conductors that allow the pressure to move more directly. Now maybe semiconductors have that ability. Maybe you could push them with electricity a lot easier. But the problem is that a plasma is going to heat them very quickly, and that's going to cause them to not be superconductors anymore. So it gets a little complicated. But anyway, that's going a little far afield. I just want to get to the point of understanding that momentum, so mv is clearly just pounds. It's clearly just weight. And so it would be kind of silly for you to think that you could have these different ways of saying how much does it weigh. Whether I put the scale here and read the weight, or whether I put the scale underneath it and read the weight, right? I mean, what's the difference? Right? So if the thing is moving, it's the same thing as it having weight. And moving, falling on something is the same thing as sitting on something. It means you just have weight. The bottom line will be is that you're going to move the little arrow on the scale. You're going to move the little arrow a certain distance on the scale. That's all that's going to happen. That's the only difference between dropping it from here and just having it sit on the scale is where the needle is going to end up going. And the needle is going to be a measure of its pressure, the pressure it can impose. And the pressure will be its total weight. Now, as long as it doesn't deform. So the trick is when you drop butter, it might deform. It might go squish a little bit here and squish a little bit here, and so you're not going to get an accurate reading. So you have to make sure it's very cold butter. But anyway, the point is once you have this, once you have a comparison that tells you how much weight, okay, equals a joule, then you can just do this. Then you can just understand it all as just being weight, pounds, kilograms of pressure. And to me that makes the whole thing so much more intuitively understandable, to understand all of this movement stuff as just being the consequences is that you apply pressure, that you gain weight by moving. Now you gain weight, you don't gain mass, you gain weight. Weight and mass are different. Weight is a measurement of your mass. And so the velocity is in sense increasing the significance of your mass. It's making your mass more meaningful. It's amplifying your mass. You amplify the mass with your velocity. A way of saying it anyway. I don't know if it's a perfect way, so don't quote me, so to speak. All right, so anyway, kilograms meters. In traditional physics, a joule is defined as a Newton meter, or kilogram squared second squared. Well, again, all this crap is just totally unnecessary, because if you just put it into something like a watt and just say a watt is a second, okay, a second of electricity, that's pressure equal to a joule, and so it's always just pressure. So you can just say if a watt and a joule are the same thing, those things are the same thing as a piece of butter hitting the ground after traveling a meter. So it's a certain amount of weight. All right, anyway, a Newton meter is also defined as work. So we know work is just, it shouldn't even be complicated. Work is always just this transferring thing. Work is the process of transferring my motion into something else. I have to produce the force, the motion, to cause something else to move. Now I can use a catapult like my arm. I can use a mechanism, physical mechanism that I move that causes the other thing to move. Or I can use an actual force in the sense that I can use, what's a good example? I mean, I can't make magnetism. I can't turn it on and off without pumping electricity in. So, I mean, I'm always going to have to apply the force in some other form. But, I mean, you could sort of understand that the electricity makes the motor turn, makes the catapult swing, makes the object fly. It started with the motion in the wire. It started with the pounds, the pressure, the voltage, and the amperage, the wattage that you put into the wire. Okay, a Newton meter is also defined as work, or force times distance. So again, this force times distance can't mean anything to anybody reasonable, because they know every experiment isn't over distance, that the transfer of the energy between two steel balls in a Newton's cradle is so minute and so fractional that you couldn't even measure the distances of the actual transfer. So it would be totally irrelevant to any meaningful equation. So that's a crap equation. It just doesn't mean anything. Obviously, you measure velocity based on taking a set amount of time or distance to do it. You can do it by distance, how far did it travel, or you can do it by how much time did it take. But the point is yeah, but it doesn't, that's, you can't use that scale and say that scale always works, because that's exactly what got them into this problem. They think that everything's like gravity, where light things travel faster through it because, frankly, the force of gravity imposes less force on lighter objects. It resists lighter objects dramatically less. It applies less force on smaller, just like the rain hits smaller objects, less rain hits them. So if you can shape the object, its mass would be your shape as gravity sees you, then you can have less of it affect you. It's just a fact. Shit. Times distance, taken FD. So then you are okay with energy with the units kilograms seconds. I'm just saying it's just not an issue. This whole seconds squared or seconds, it doesn't involve it's not the real unit, right? We're talking about mass, and velocity has the seconds already in it in terms of how you measure a velocity. So there's no absence of the pieces you need to understand it as a unit. It's already in it, And then all you can do, you can say it weighs a certain amount of pounds, and then you can understand that, well, how I bang into the object, that is, where those pounds, how much surface area I hit the thing with, will decide how much of that momentum can be transferred, how much of those pounds, because it's going to be transferred through that little space, that little piece of, all the pounds have to go through that little bit of interaction. And so that's why it can look very energetic, is because, even when two cars hit, they hit piece at a time. And so the whole momentum of the car is being transferred through the little pieces at a time. So there's a whole pile of pressure bending and twisting things. Where if it hits, head on and it's spread over a larger area, the deformation will be completely different. So depending on how you hit something will decide how much of the energy is transferred through deformation, and how much it would be transferred in heat and all these other things. So, but it's just transferring weight. And velocity is essentially just magnifying weight. Your weight is magnified by a percentage of your velocity. So the more velocity you have, the higher the percentage your mass is being magnified. And that's a simple and easy way to understand it. So you're just taking the 100 grams of butter that has it's 100 grams. And wherever I put it, it's 100 grams on a surface. It can apply 100 grams of pressure. But once I start moving it, I'm now giving it more momentum. I'm magnifying its weight by the percentage of its velocity. And now when it hits a surface, it's going to have 4 times or 10 times or whatever the number will be of its original weight. And that's a simple way to understand it, in my opinion. Insanely simple. I mean, it makes it so much easier. I mean, all this jargon you people want to get lost in. There's just like I said, the very fact that a newton is only 1/10 of a kilogram kind of already gives you away that your units are already sort of broken. Because you have to understand that, the newton is based on 1/10 of a kilogram, right? So it's already sort of, it would have been much better to have the newton be the kilogram. The actual kilogram, the weight of a kilogram should have been a newton, or something like that. It would have been better if the standards were the same. And again, the joule is just now, it's, whether you drop it a meter or drop it a half a foot or whatever the standard's going to be. So it's just a standard. And then that can just be, like I said, even if the joule was some other number, you could still convert it into pounds. Because all you have to do is know what 102 grams hit from a meter's distance. If that's a joule, like I said, then you have that number. You already have all you need to know to convert it into any other circumstance. So every circumstance, you can just take the butter standard. What's the stick of butter do after it drops 1 meter? How much does it weigh? How much was it increased in terms of its mass? And you can just use that everywhere else. And so you can just say the train has 968,000 sticks of butter worth of pressure. Newtons. So you can always convert it into newtons, or convert it into joules, or convert it into watts, or convert it into pounds. Weight. So it's all just pressure. And once you understand it as pressure, you can understand you can't use it 2 places. The pressure hits something and exchanges, then the exchange is done. You can't get the pressure back. If I'm using my pressure, I can't use the pressure twice. I can only use the pressure to do work once. So their whole theory of this, babble about all this extra energy is just that. It's babble. It doesn't have any coherency to there's no good reason to believe. There's no experiment that proves it. So maybe that's what I'll just do. I'll take a break and come back and we'll just go over what I have already shown in experiments and what can be deduced from the available experiments. Yeah. Alright, should be back and such. So I have shown the experiment. It basically tells you enough. So you have 2 carts and you have a consistently compressed spring. That is, this distance the spring is compressed is the same. And you shoot the 2 carts of equal mass and they leave with exactly the same velocity. And we'll call it velocity of 1. Well, we'll call it velocity 10. Alright, so they both leave at 10. And so then I make this cart twice as heavy. Alright, so now it's a 2x cart. And then I do the same exact thing. Alright, and what happens is this cart leaves at 10. So what's on this side of the spring means absolutely nothing to this cart. However this force mechanism works, it's clear that it's always giving the same energy this way and the same energy that way. And this cart leaves at 5. Alright, and it's a little tiny bit less than 5. So when I showed Professor Lewin doing the experiment, the numbers were something like 144 or 153 or something, and 72. Okay, so it's like 153 and 72. And the 153 is basically telling you, like, this would be 146, right? 7 times 7 is 14, 4, okay. And so it's a little bit higher, which means the thing took longer. That means it was a little slower. So it means that this left really at 4.97. Okay, so clearly the momentum was conserved in the sense that it's twice the mass. Momentums were, it's pretty close, and you can sort of understand that there were a little bit of losses because of the heavier object. The wheels probably had created a little more friction, so you lost a tiny bit of the velocity to the fact that the heavier object creates a little more friction and blah 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 blah, because it's the same cart with the same wheels, and obviously there'd be more tension on those wheels, more friction, more weight on the track. And so that would account for it. That little bit of loss would account for the fact that it's a little harder for physically, because we don't have a perfect frictionless environment, that you lost a little bit because of that. But there's no way to explain the facts, okay, that basically you're now saying, so if I do the math by, their formula, it says that these two had 100, okay, units of energy, and then these two has 100 over here, and I only got 50 over here. So I lost half the energy. Now, there's no way you could figure out how you lost half the energy. I mean, it's clearly not evident that you lost half the energy. And there's every evidence, anybody logical would say that, yes, this 2x thing going 5 will compress another spring exactly the same amount as this one. So there's every reason to understand that momentum works. mv squared doesn't even come close. 1/2 mv squared, or vmv, divided by 2, fails to follow the energy in any rational way. And the simple argument is this experiment is telling you all we need to know. It's telling us that, if I just had the spring shooting off of a fixed wall, okay, that would be the maximum amount of velocity I could create, is the speed of the spring alone. But that the real momentum is always still going to be just 100. That's all you're ever going to get in this direction, and you're always just going to get 100 in this direction. And that's all that's ever going to happen with this spring. The spring is always going to produce exactly the same energy in both directions. And it doesn't matter what's here, here, here. None of this matters. It just matters that the spring is going to produce 100 units of energy, 100 joules you could say, or 100 pounds of force in both directions. And they don't have any theory contradicting this. They don't have any experiments that explain how this is. You lost half the energy? How did I lose half the energy? I'm just pushing carts. Where did half the energy go? I lost half the energy to the extra friction? I mean, it's a ludicrous statement. Of course I didn't. Of course that didn't happen. The wheels didn't break. They didn't catch on fire. How could I lose half the energy? Half. I mean, a gigantic. The energy to move carts. I mean, the carts are still moving pretty fast. I mean, it's a lot of energy to lose. So how did I do it? How did I lose it? Well, of course I didn't lose it, because by momentum standards, this twice as heavy going half as fast is just as much energy. So everything is conservative, everything makes sense. And if I use their formula, none of it makes any sense. How did I, if this was the right answer and there was only 50 joules going this way, then how did I get 100 over here? How do I make those extra joules? So, I shouldn't have to go over and over this, but yeah, apparently I have to. And that's tragic. And I wish there were a lot more better. I mean, I have gone through, literally hundreds of kinetic energy videos, and they're all so immature, childish, silly, and terribly useless. It's just sad that they only do the experiment in these certain ways to prove certain points, and they're always doing it in the way where they're never doing the real comparison. They'll talk about bowling pins and knocking down pins. I mean, there was even that, Bill Nye has some dopey video on momentum. He talks about knocking down pins, and they pick up, they talk about the 8-pound ball and having to, and instead of actually doing the experiment, they, joke it up and have him slide down the alley and knock over the pins, his whole body. When, that would be the great argument is, well, you're supposed to have twice as much energy. So if you use the light ball, you're supposed to be able to knock down twice as many pins. Well, why don't you show that happening? Why don't you show how, wow, look at this kinetic energy formula really works. It really predicted the results, which is I'll knock down twice as many pins if I use this lighter ball, which is just doesn't work, doesn't happen in the real world. The formula doesn't predict accurately, and yet they just keep defending it. And you're like, what are you defending? These are ludicrous thought experiments. Again, the 10-ton train, the 5-ton train going 10 miles an hour connects to another train. So now it's a 10-ton train going 5 miles an hour. And they think it lost half its energy. Half the energy of a big giant train moving at these velocities. They think half the energy just disappeared to noise and sounds and sparks. They think if they add up all that stuff, they'll get half the energy of the train. I mean, get real. It doesn't have any chance of being a rational perception of reality. And again, this was the excuse that Leibniz had to keep making. In every inelastic collision, he had to keep just saying, well, it all disappeared through heat. He didn't say heat because they really didn't understand heat yet. But he said, of misdirection. There's a bunch of the little bits inside are going the wrong way, and that's where all the heat is. That's where all the energy went. That's where all the momentum went. That's where all the kinetic energy went. But there's no evidence of that. These are very efficient transfers. You just can't make the logical argument, okay, that the spring lost half the energy pushing the heavier object. And that if I push it against a wall, it lost all of the energy. Didn't lose it. The pressure's in the thing. The pressure was imposed. It felt the pressure. Just like we are pushing into the ground right now. Do you think we're not pushing into the ground? Do you think you would feel the earth pushing back if you didn't first push into the earth? Don't you think you first have to push into it for it to push back? You've got to know that's the way it's working. And it's not working any different for other objects. And that the key point is that the overall, the effect is an acceleration down. That's the one that keeps reoccurring, is the one going into the object. The one pushing you back keeps you neutral. It doesn't give you extra energy, it just keeps you neutral. And then you go back in again, and then you're neutral. You're negative, then you're zero. You're negative, you're zero. You're negative, you're zero. You're never a one. All right. I don't know. It's, I have to find somebody capable of discussing this in some sort of broader, where they're able to actually draw something on a chalkboard, or actually able to play a video, actually able to make some kind of argument. And so I have to find somebody willing to have this, to take the side. Go ahead. I'll defend momentum. You defend kinetic energy. And let's have the trial. Let's argue the argument. And, it needs to be done. And every good scientist should say it should be done. Because the two things are direct contradictions of each other. They don't predict the same answers. They predict fundamentally different outcomes. Come on. Why would anybody who likes science like that? A duality that grotesque and nonsensical. A gross contradiction in your logic. Why would you think that's a good thing for science? So anyway, enough of a video, I'd say. So, till the next time and such. I guess we'll play the... Alright, this has been a DraftScience video presentation and such.